Okay. Okay, so let's begin. I'm Mike Douglas, and this is the New Technologies in Mathematics seminar series of the CMSA Harvard. And today we're delighted to have Yang-Hui, who is from Oxford, London, Nankai, probably many other places.
That's it for now.
And he's a leader in this budding field of machine learning mathematical structures. So tell us about it, Yang.
Thank you very much for the invitation. It's delightful to see old friends, especially to see Mike. And so I'm going to talk a bit about the title is a bit vague. What I'm going to do is to use sort of Calabi-Yau compactifications from the point of view of string theory, sort of as a starting point before we march on to other stuff. And I think Mike told me that this is a fairly mixed audience between physicists, mathematicians, and computer experts. So I will make this talk as general as I can, and I hope to get everybody interested in this sort of direction. So let me just begin by giving a very quick overview of this tradition of the right language for physics. I mean, it's well known in the in the 20th century. Algebraic and differential geometry and topology in various combinations and representation theory is the right language for fundamental physics. When physicists talk about gravity, we're really talking about Ricci 2 forms of tangent bundles. When physicists talk about elementary particles, we're really talking about irreducible representations of Lorentz group, et cetera, et cetera. I mean, what string theory is, I mean, this talk is really not about string theory, but there's a lot of ideas that were inspired by this. We can think of string theory in a way as a brainchild for this gauge gravity geometrization tradition of just trying to translate all of these fundamental laws of physics into the right language in modern geometry. And so that's the 20th century. For sure, this is well established. But as we enter the 21st century, it's also beginning to be more and more realized that the physics community are becoming inevitably tangled with not just the theoretical geometry, the pure mathematical community, but also the computational mathematical community. And this is, I will mention a little bit later. I'll draw some diagrams. Hopefully, will convince you of this fact. But something, a lot of computational mathematicians, and especially I would like to emphasize is the SAGE Math project headed by William Stein, which is sort of like an umbrella project which tries to incorporate all of the various other mathematical software from fields of computational algebraic geometry, from number theory, from finite group theory, representation theory, just have it all interaccessible. So, but what's interesting is I would say in the last 10 to 15 years, these things and the databases maintained by this software has become really a part of the theoretical physicist's tool, right? For years, the theoretical physicist's favorite go-to thing is Mathematica, Wolfram. But now these things have been beginning to seep into the theoretical physicist's sort of toolbox. So this is an exciting era for the 21st century. So we see this is at least historically where we're going with this. So let me just go back to just give a 1 second slide of what superstring theory is and why this gives such interesting problems in geometry and computational geometry. And then hopefully I will convince you will also be interested in things like data science. So just a one-liner, and I apologize for the experts. String theory essentially is this a high-dimensional unified theory of quantum gravity. And we have to reduce dimension because we don't live in 10 dimensions or whatever dimension it is, 10, 11, or 12, but we live in this 4-dimensional world. So we have to reduce dimension, and there are 2 standard scenarios where this happens. You can either propose that the extra dimensions are tiny, 6 extra small dimensions, or you can do some large 6-dimensional scenarios in terms of brane world configurations. So that's my one slide about string theory. And that's not what we're really going to focus here. So traditionally, and I would say that this really came about in 1984-85, which was what's called the first string revolution. And the details are not so important, but back in that time, because of these authors, people realized there is a particular naturalization of the E8 gauge group within an anomaly-free framework. And then immediately was this paper which started, what we now call string phenomenology. Right, so it's interesting that physicists were worried about a very specific problem, and that problem was: is it possible to embed our standard, our standard model of particle physics into this new promised theory, new then in 1985, theory of quantum gravity? And because of this embedding, the standard model groups naturally embedded into E8 gauge group, which came for free in the setup in a way, this was all of a sudden it became a very promising direction to follow. And one of the solutions for these extra 6 dimensions, and I have to emphasize this was the first solution I found. Of course, the full set of solutions is much bigger, right? Since then, people have realized that a whole host of new geometries and new non-geometries which are possible, but nevertheless, it was possible to find one very interesting class of solutions for this extra 6 dimensions, right? And then it was in particular, these solutions were called Ricci flat and Kähler manifolds. Now this is very interesting because to the 1980s physicists, they knew what Ricci flat was. This is just flat manifolds, manifolds which have a flat Ricci curvature because of the experience with vacuum Einstein equations in GR. But they didn't really, stumbling upon Kähler condition was a little more strange. So these are for Kähler, for non-experts, Kähler manifolds are just simply complex manifolds in a way that whose metric can be written in terms of a double derivative of a potential. So fair enough. So physicists were, because of string theory, stumbled upon this new class of manifolds that really never really emerged into the physics literature before. But of course, mathematicians at the time were thinking about this in a way. There's a long tradition of what mathematicians were thinking about in terms of a similar type of ideas. So this really goes back to Euler, Gauss, and Riemann, and in particular the work of the Riemann what's called the Riemann uniformization theorem, which essentially says there's a trichotomy of compact smooth surfaces in complex dimension 1 or real dimension 2. So in particular, we know that surfaces are famously, this was realized by Euler at least, that famously they're classified by the number of handles, right? A sphere, the surface of a sphere has no handle, the surface of a torus has 1 handle, etc., etc. Riemann uniformization essentially says this splits 3 ways. There's this structure in the middle, the torus, which if you think about it is essentially flat. And to the left of it is essentially positive curvature, and everything here is negative curvature, right? So they had this beautiful set of stories in complex dimension 1, where this boundary case of Ricci flatness, well, now we call it Calabi-Yau, but in a way you should think about this as Ricci flat. And then you have this positive curvature, which in complex geometry you can think of these as Fano varieties. And then the negative curvature ones are varieties of general type. It's an incredible theorem. Well, let me not get to that. Let me get to that in a minute. So the classical theorems of Euler, Gauss, Riemann, Bourbaki, and so on, tries to relate various topological and combinatorial stories with analytic stories for these 3 classes. So for example, this is the beautiful, this sequence of equalities really is, it's a beautiful set of stories that goes, has at least 100-year history, where the Euler number, which is a purely combinatorial object, as the alternating sum of the Betti numbers, is equal to 2 minus twice the number of handles in your object. And then Gauss's theorema egregium is the realization that this purely combinatorial object is also equal to 1/2 pi of the integral of this curvature. And then I guess people like, this is a much fancier way of writing this integral, is to think of this as an intersection theory of Chern classes with the manifold. So this is a very nice story in complex dimension 1 or real dimension 2 that really goes back to at least 100 years. So of course, it's way too much to hope for that something this simple would hold for arbitrary dimension. So that's why mathematicians were thinking about this for so long. But at least for Kähler manifolds, an analog of this beautiful sequence of equalities was at least conjectured by Calabi in the 1950s. I'm not going to get into details of the Calabi conjecture, which essentially says that for Kähler manifolds, the curvature is in a way controlled by the Chern class in this way. So that was a conjecture of Calabi, and it took at least 20 years before Yau proved it, and for which Yau received the Fields Medal. So you can see why this is a very important direction for mathematicians as well. So the motivation behind this is in a way the generalization of this beautiful story in complex dimension 1 to arbitrary dimension, where you think about this Ricci flat boundary case of dividing positive curvature and negative curvature. So there are theorems which say that final varieties in each dimension is the topological type is finite, and there's a conjecture which says a Calabi-Yau in this boundary case of zero curvature is also a finite topological type. Whereas we know that general type, the negative curvature cases in every dimension, is just wildly, untamably complicated. So that's why the mathematicians were thinking about this. And it just so happens that this is a story that Philip Candelas tells me is a great story, that one of the authors here, Andy Strominger, happened to be sharing at least a corridor office with Yau in the Institute in 1985. So it's perfect that physicists and mathematicians who would otherwise never have spoken to each other were precisely around, in the same space-time point in 1985. So in fact, I believe that even the word Calabi-Yau as this boundary case of Ricci flat Kähler manifolds was actually coined by physicists. Before, they were just called Ricci flat Kähler manifolds because of the proof of the Calabi conjecture. So this is totally cool. So I think one of the very first questions that Andy asked Yau was, can you give me examples of these things? Because these theorems of these conjectures of Calabi and these theorems of Yau were highly non-constructive, right? So just give us some examples, right? This is the sort of thing that algebraic geometers find embarrassing. They don't want to give examples in public. They only do examples in private. So nevertheless, here's a theorem, which is if you take a generic homogeneous degree n+1 polynomial in CPN, then this hypersurface is Calabi-Yau of dimension n-1. So you can easily show this by adjunction to get the vanishing Chern class. So this is really nice. So in complex dimension 1, our Calabi-Yau, remember, was just this thing, right? This boundary case of the torus. You can realize this immediately as a cubic in CP2. And this is a classic object that's known to, I guess, Weierstrass, that this is the elliptic curve realized as the cubic in CP2. So that's complex dimension 1. Complex dimension 2, you can realize these are K3 surfaces. You can realize this as quartics in CP3. I mean, this is not the only way to do it, but you can do other embeddings, but this is a standard way to construct them. So immediately you get 5 other ones for free. You can get the degree 5 in CP4. This has been affectionately known as the quintic. So Mike has done a lot of really beautiful papers on the quintic over the years. So, but this is still, I would say, the physicist's favorite manifold in a way. The favorite complex manifold. And then the rest is just partition problems, right? So you can look the intersection of 2 cubics in CP5, because 3 plus 3 is 5 plus 1, and then 5 minus 2 is 3. So you want the complete intersection condition. And then you get 2, 4 in CP5, 2, 2, 3 in CP6, and 2, 2, 2, 2 in CP7. So these are examples of complete intersections which are realized in a single projective space. So this is just a partition problem, as I said. It's interesting, I want to emphasize, complete intersections in general are rare. The fact that, I define some complex projective coordinate and I slice it out by polynomials one at a time, if, each slice cuts dimension one down, it's a very special case. In general, you can have multiple intersections, many polynomials, and they don't have to have this condition. To emphasize again, it is a theorem that any Kähler manifold can be written as a Kähler threefold can be written as non-complete intersection in CP7. So in some sense, if you want to classify all possible Calabi-Yaus, or even classify all possible Kähler manifolds, all you need to do is to write sufficiently complicated polynomials in 8 variables, which are projective. But nobody would ever do this because you could end up writing 7 million polynomials which don't intersect transversely. But nevertheless, it's at least theoretically possible. So that was cool. So so these are manifolds. Interestingly, and as I said, there is this tradition of translating, physics, whatever you're doing with physics, into mathematics, and that was one of the highlights of this paper, was to translate the number of generations of particles to topological invariance of this manifold. I'm not going to get into the details of these representations, and certainly we've gone way beyond this. We've generalized much more beyond this, even within this setting of string theory. But nevertheless, back in 1984, they posed this as a very specific problem, which is the number of generations minus the number of anti-generations of particles has equal to 3. That's an observational fact from CERN. And therefore, because of this translation from algebraic geometry, they asked, card-carrying geometers like Yau, can you give me a compact, smooth, Calabi-Yau, Ricci-flat Kähler manifold, which had Euler number plus minus 6? But as far as I know, this is the first time, physicists have ever asked the algebraic geometry community so precise a question. And so that's fine. So Yau told Andy, these manifolds, but immediately you can check that none of them have this property. They don't have Euler number plus minus 6. The quintic, for example, has Euler number minus 200, which is very far from minus. If you just naively put things on the quintic, you're going to get an E6 gut theory with 200 generations of particles, which is not that exciting. It's not a universe which we want to live in. But fine. So if the immediate ones didn't work, let's just bite the bullet. And then this is really interesting that in the course of something like 10 years, physicists took on this challenge of creating more and more databases of Calabi-Yau manifolds for this very specific reason, to find Calabi-Yau manifolds with specific topological properties. So the first challenge was headed by Philip Candelas and this is no relation to me. I was still in primary school then, and Tristan Hubsch and Lutgen, Schimmering, Berglund, and so on, so forth. And what they created here was what's known as sissies. It's a very beautiful name for complete intersection Calabi-Yaus. So it's not important what these are, but we can just basically look at these as complete intersections, not in a single projective space, but multiple polynomials in products of projective spaces. So each one of these columns is a multi-degree polynomial within a product of these. And Calabi-Yau conditions translate to the fact that each row sum is this integer plus 1, and so on and so forth. So for example, quintic is a very trivial example of a sissy, and you can just write this as the degree 5 polynomial in CP4. And then there are other ones you can do products of it, such as things like the Tian-Yau manifold, and so on and so forth. What is really interesting, and especially for this audience, was that when they were classifying this, so they reduced this problem in algebraic geometry to a purely combinatorial problem. How many matrices are there that have this property that each row sum is one of this, and such that the sum of this number is 3 more than the sum of this? There's certain combinatorial conditions, and then up to permutation and up to some splitting equivalence. And they very quickly realized that this problem was already not doable by hand. right? This is not, this is 1986, 87. And then they realized very quickly that you got to do this not only by, not is it not doable by hand, you really had to recruit the supercomputer to do it. So luckily they had the CERN supercomputer available. Algebraic geometers would never dream in 1986 to ever use the CERN supercomputer. These days they do, interestingly. So I'll mention a little bit. There's a whole group headed by Alessio Corti in London who does this sort of thing. But so fine. So they use this supercomputer, and then they classify these configurations. Unfortunately, the only surviving forms of this data are in two forms. One is in paper printout form in Philip's office. It's about this much, and nobody wants to read it. And the other form is a magnetic tape format in Andy Lutken's format office somewhere in Norway, and nobody can read that either. But luckily, we have resurrected this data, and now it's freely available online. So if you want to play with it, this is a data around about 8,000 configuration matrices of 266 distinct Hodge pairs and 70 distinct Euler numbers. So this is kind of interesting. One of the first things that these people realized was that this is actually a biased sample. The Euler numbers for all of these manifolds were all negative. But by the late 1980s, people knew about mirror symmetry, which is something that switches this pair, so that would map the Euler numbers to the negative of the Euler number. So whatever this set is, it's an interestingly biased one. So Philip and Monica Linke and Schimmerink took the challenge. So these things basically go as 5-year plans. So this is a perfect thing for grant proposal. They happen in 5-year chunks. By 1990, they realized, well, let's have a more balanced set. So what they did was to weight the projective space, weighted P4. So the classification here then just comes down to how many 5 vectors can you write, such that there's a single hypersurface with the degree sum of these weights. So it's again a combinatorial problem, and these guys classified again came around about 8,000, and this is now a much more balanced set of Euler numbers. So that's kind of interesting. And again, chunks of 5 years. The real impressive work that was done by Kreutzer and was done by Kreutzer-Skarka from the mid-1990s. So that took about another 5-year chunk, which is due to a theorem of Batyev and Borisov. And the details not important. Is another way to generalize weighted CP4 is just to take a toric variety. But the Batyev-Borisov theorem said if you take a toric variety constructed out of a reflexive polytope, then the hypersurface in that is Calabi-Yau. So this is another general theorem. So what is a reflexive polytope? This is really, really interesting. This is a problem that you can explain to a high school student. And when I take like a summer student from high school, this is a perfect problem to explain to him or her. So what is a reflexive polytope? Let's do in dimension 2. Dimension 2, these are reflexive polygons. So these are polygons which are lattice polygons. So each point is a lattice. And so for dimension 2, all it is just how many lattice polygons can you write with only a single interior lattice point. That's it, up to GL2Z. So the fact there are only 16 of this was known to people like Fano and Del Pezzo back in the 1890s. So just draw it. You can convince yourself. I guess it's a systematic way of drawing this, that this is the only way to do it. So, but the next number, which are polytopes in dimension 3, also, by the way, so if you constructed these toric varieties, you take the hypersurface in those, you're gonna get elliptic curves as Calabi-Yau. So these are 16 very distinguished elliptic curves, which are very, very interesting. And I think they haven't really been explored that much by the math community because it's a bit esoteric. And I'm sure there's a lot of if anything, there should be a lot of deep number theory hidden in the 16 distinguished elliptic curves. But anyhow, but the next number, right? You want polyhedra in 3 dimensions, which have the property there's a single interior lattice point, such that all the bounding hyperplanes are distance 1 from this. You can explain this to a high school student. How many there are, and nobody knew. From 1890 until the work of Kreutzer-Skarka in 2000, that's 110 years. Nobody knew what the next number was. And then this number turned out to be 4,319. So you can convince yourself, I don't get draw. I mean, you could, do this on a big computer. And that's the next number. But those things will give Calabi-Yau twofolds, which are K3 surfaces. Again, very distinguished K3 surfaces. But the one that physicists at the time wanted was the next one up. How many dimension 4 lattice polytopes have the property that they have a single interior point and all of the bounding hyperplanes of dimension 1? And this number was astounding. And Kurtz and Skarka spent the best computer they had at the time and ran it for 6 months and produced this crazy number that's been cross-checked now by the math community. So all of a sudden, your Calabi-Yau threefold zoo went from 5 examples to 473 million and growing still. What is really, really interesting is I've talked to every combinatorics I can find on the face of the planet. Nobody knows what the next number is, and nobody even knows the theory to even try to predict the next number. There's no known generating function. The problem is so simple. How many lattice objects are there such that there's a single interior lattice object and all the bounding planes are distance 1, up to GL, and Z? And nobody knows even how to solve this problem. If you can solve that problem, it would be great. It would be one of the great breakthroughs in combinatorics. Skarka last year did an estimate of the next number. It's at least 185 billion, at least. But so well, I don't know. But it would be so cool to find some kind of a generating function. Obviously. This reminds me of the early days of I think Mike would really appreciate it. It reminds me of the early days of the counting rational curves. What's the next number? And physicists came up with the next number. But so far, no one in the combinatorial community or in the algebraic geometry community has come anything close to what the next number is. So now back to the physics. So this really impressive work of Kurtz and Skarka, which answered a lot of problems in combinatorial geometry. And now all of a sudden you have 30,000 distinct Hodge pairs. So just to make a remark, no construction of connected, smooth, compact Calabi-Yau threefold has ever broken this bound of 960. I mean, it's kind of consistent with the conjecture there's a finite topological type of, but nobody knows why 960, whether it is the bound, we don't know. So it'll be cool to study this just in its own right. So here's something I ripped off from the internet, which I love very, very much. You can read it. But basically, we think of the age of data science as like, this decade, but really, I mean, for theoretical physics. But of course, experimental physicists were thinking about this kind of thing. I think the first meeting of machine learning, for the sake of Higgs detection, that happened in 1997, if I remember correctly. But in terms of theoretical physics and mathematics, it's really back, really goes back to the mid 1980s as well. Just in terms of the ideas that people were thinking about. So. Today, people are still mining. There have been lots of various combinations of collaborations, still data mining this 4,073 million. Because even by today's standards, this is respectably big data-ish. So, and I just want to emphasize the actual number is actually much, much bigger because this is just polytopes. Different triangulations of these polytopes would give different, potentially different Calabi-Yaus. So with Brent Nelson and friends in Northeast and Jajal and friends, we tried to triangulate them by brute force up to H1 equal to 7 and got maybe like 2 orders of magnitude more. But that's just only this tiny little tip here. Here is a plot of all of the Hodge numbers. They're 470, they're almost 500 million points, but 30 distinct Hodge pairs, right? So this is a log density plot of this. And if you want, the most concentrated ones, at least within this data set, is the 2727 self-mirror manifold. And we don't know why, but it is 27 3 cubed. It's a very nice number. And Waddy Taylor's has done some very nice work in trying to explain, why are these bits missing. And people like in the Cornell group of Mike Steelman and friends and try to explicitly triangulate all of the ones over here and so on. So this is still very much work in progress. Just trying to understand this quite massive database of Calabi-Yau manifolds. So just to reassure people who are not physicists that, okay, fine, you got all these Calabi-Yau manifolds. Is it even possible to construct something that's even remotely like the standard model? I mean, how do we know we're not even looking at a null set? It's possible, but at least so there's some initial work in the Penn group which show that you can actually find the exact MSSM from this construction. And just to mention, more recently, there's this really nice work of Anderson and friends, which showed about 200 in 10 to the 10 bundles over Calabi-Yau manifolds. You can find exact MSSM. So you're not looking at sort of null data sets. There's a more recent estimate just from extrapolation that I was doing with Andre, is that if you just extrapolated the CICY data set, you could get something like potentially 10 to the 23 exact MSSM particle content. This is about 1 mole of standard models. That's what Tristan Hoops says. But not to worry, this number is supposed, you can imagine this is just particle content. If you want to slash this down further by Yukawa couplings and other particle masses, you get much bigger reduction. We don't know why. I mean, Philip still thinks that there's a selection rule, even within the landscape of Calabi-Yau manifolds, of what, whether our universe is special. So Philip likes to think that things are special, that we live in a very special world. It would be a very, very beautiful idea if indeed we could find a selection principle among even this landscape. So, and as I said, this program, in this 5-chunk program, kind of got distracted in the mid-90s for a good reason, because by the mid-90s, the string landscape, as I mentioned, grew enormously with D-branes, M-theory, and so on and so forth, and flux compactification, all other possible scenarios. So this Calabi-Yau landscape, the traditional compactification scenario, became much, much smaller. But nevertheless, this is entire explosion, and one of the first statistical estimates of a possible universes that come out from this scenario was done by Frederick and Mike. Just estimate, what's the probability that we hit our universe, and then there's this old paper of KKLT which sort of as a back of envelope estimate, at least at 10 to the 500 different types of fluxes you can put to get different types of universes. So that's why this this Calabi-Yau thing became only a part of a much bigger picture. So in a way, for non-string theorists, I like to phrase it in this way. Now, string theory trades one very hard problem, the quantization of gravity, by another very hard problem, which is how to find the right geometry. And I think in many ways, I think the second problem is much more interesting, because the first one is a purely physics problem, and the second one is a physics, a math, and a computer science problem. So it's a much more interdisciplinary question. So just to summarize where we stand today, which is, there's the good thing being, in the last 10 to 15 years, as I mentioned, physicists have been working very closstein with computational mathematicians, people like Mike Stillman and Dan Grayson, Howard Shank, and William Beilstein, just to bite the bullet and actually compute these things on computer, and get them organized into databases, and they're freely available. We're not Stephen Wolfram. We make things open source as much as possible. And you can, if you're bored and you can't sleep at night, these are just some links you can go to, just download them. The typical databases are about 10 gigabytes, so not totally crazy. And you can play with them in however you want. That's a good thing. The bad thing is that almost any of these computations is hard in a technical sense. If you want to do toric geometry, the dual cone or dual polytope algorithms is exponential running. Triangulations is exponential. And if you want to do anything in computational algebraic geometry, the first thing you want to do is to put everything to Grosvenor basis. But the Grosvenor basis is famously known to be a double exponential in complexity with respect to the degree of variety. As expensive, I can punch in, a quintic manifold with maybe 10 terms, and punch that into Sage, call Macaulay, and compute its cohomology completely. And that can be done in seconds. But if you just put like a slightly bigger one, like, like a product of two varieties, and then the Grosvenor basis will grow so fast, you'd already take, days before you can get an answer. So that's an unfortunate fact. So to just feed in the entire landscape, or even to sample enough part of the landscape and just punch it into Sage is doable, but it would take the amount of computational complexity will be so overwhelming, you probably won't find the right universe. If that's what you're after, if what you're looking for at the end of the day is just looking for the right compactification, this is not a practical way to do this. Right? So that's the good, and there's the bad. And then you ask, well, what about the whatever? And how about borrowing new techniques from the big data revolution? So if you think about it, a typical problem in string theory and algebraic geometry is if you take some integer tensor input and you spit it out some integer output. This is a typical problem. It's typical because we don't have any metrics to play with. I'm going to mention a little bit of metric, and I think Mike will like the thing on metric later. But typical problem you'll find in topological invariants from configuration matrices, right? Or you'll find it like things like Hodge numbers or Euler numbers from polytopes. Right? So one of the questions that I asked myself was just exactly this. Is it possible? I mean, this seems like a really simple thing to feed in to some machine learning algorithm. So that was the thing that was experimenting, and I was surprised to find that this was actually doable. And so my friends were so there were 4 collaborations in 2017 that were thinking along very similar ideas. As Son and Krefeld were thinking about Calabi-Yau volumes. Fabio Vuela was thinking about genetic algorithms to find bundle cohomology, and the northeastern group of Jim and Brandon friends were thinking about F-theory landscape, how to find this. So again, to give you an overview, this is kind of fun to see this. Let's just go back to see the sort of the trending in annual conferences in string theory, right? So 86, that was the first string conference. Well, not surprising because that was right after the string revolution, the first string revolution. But you had to wait until 2002 before the first branch off of the string pheno conference. And then there was the 2006 to 2010 String Vacuum project. I think Mike was part of this NSF grant. Keith Dinnes and friends were doing this. And then 2011 was the first string math. It's kind of interesting that you got to wait. I mean, of course, string math existed long before, but you had to wait until like 2011 to this decade for the first string math conference. And 2014 was the first annual string session in the SIAM thing. This is my proudest contribution to the field, was to make sure that there's a voice for theoretical physicists in the SIAM, which is a Society of Industrial and Applied Math community. So every year now since 2014, we've been organizing this with Mike Steelman and friends, just to make sure, here are our problems. We give you very computationally difficult problems, help us, kind of thing. And 2017, because of those work, so now there's a new branch off. It's now known as string data, which is kind of fun. I think some of us are going to that next month. So back to this. I don't need to. I think this community we don't need to go into the details of machine learning. But what I want to basically emphasize is that the typical machine learning problem is to recognize the digit 3. For example, here's the Google rips off this 3. Which I think in the NIST database, these are represented as 28 by 28 by RGB value fits. So this, you can think about this as, well, here I've done it in grayscale. So it's 28 by 28 by 1 of 0 to 1 grayscale images. So the interesting thing is, if you look at the typical SISI computation, here's a SISI. This is a complete intersection of 8 multi-degree polynomials in CP1 times CP1 times CP1 times CP1 times CP1 times CP2 3 times. And sophisticated methods have taught us to compute that the number is, the H11 of this is 8, and the H21 of this I think is something like 64, whatever it is. and we know how to do it, and people have been biting the bullet to do it. And you can, I refer you to Hoop's wonderful book called The Beast Theory, because these are beasts you want to do. And there's very precise method to do it, and the computation complexity of this is double exponential. So what you do, you chase exact sequences until you blue in the face, and then you finally get a number which is 8. But this is this is essentially the association rule, no different from how 3 should be associated. This image should be associated with the number 3. So here is a image for this thing to be associated with the number 8. And of course, this is the perfect problem because we have data. We have 8,000 points because of the CC data set. So what you can do is simply you take the 8,000, you enhance them because we know the equivalent up to permutations. So you enhance them up to, say, 100,000 by permutation equivalence. And that's important to build that in because these equivalences are part of what the machine needs to know. So then you run this. So the one that I did was just a very simple multilinear perceptron, just some feed-forward neural network with sigmoid activation functions. Nothing fancy. And that kind of worked very well initially. And then with my student Kiran and my friends Jajala Mishra, we did a more refined classification. Here's a classifier problem. The H11 goes from 0 to 19. You can do a classification problem to see how this goes. You can see this within the learning curves. So up to 80% valid, 80-20 validation, you get to about 90. It's not great, but luckily, more recently there's a much more serious and detailed work by Urban Finatello, which used a convolutional net for these images, and they were able to get something like 99.5 accuracy for this database just by literally looking at images of such a type. So this is kind of interesting. So and then more recently, I was playing with Andre Lucas on how to do with other manifolds. There are CC4 folds, which also gave high accuracies. So now you can see other fun things you can do in geometry. So with Lee.
Quick question. Yes. So did you say you used the CNN to do it?
Urban and Finatello did. I didn't. I simply used the feed-forward network. So it was something I remember the details. What I used was something like 3 layers of a complete linear layer followed by some sigmoids, and then another linear layer. Then I do summation and round and integer round. So
that gave you 99% accuracy?
No. That I didn't. That gave me, this kind of accuracies.
Oh, so got it.
Yeah, the Urban Finatello result, which is a more recent one, which they did use CNN, and you would imagine that image processing should be done by CNN.
Oh. So sounds like they used the Inception network. Is that right?
Yes, that's right.
Okay, got it.
So yeah, so you can do other kind of fun things like how do you distinguish elliptic fibrations within Calabi-Yau? So at least within the CC data set, this one behaved much better. Like at 50%, you're almost up to 100% accuracy in terms of distinguishing elliptic fibrations. Again, here we also used a very simple feed-forward network. So just to give an overview, I mean, I can't possibly summarize the lot of progress that's been happening in string geometry. Various things, Fabi Rula did genetic algorithms for bundle cohomology and the Northeastern work, and there's now a whole program of machine learning in the Kreuzes-Schkalka database. Of note is this nice paper of Brody, Konstantin Lucas, where they were able to just map out, just use machine learning to map out regions in moduli space for surfaces, and they were able to predict the exact regions for transition, and hence conjecture an exact formula for line bundle cohomology, which then they use traditional methods to prove. So that's a kind of a very nice way for conjecture formulation. So here's something interesting you can also do, which so far I have said nothing about metrics. These are Ricci flat Kähler metrics. The reason I haven't mentioned anything about metrics because no metrics is known except for the simplest cases, the non-compact cases, and tori basically. And so there's an algorithm of Donaldson which at least efficiently converges towards the Ritchie-Flat metric. And I think it was Douglas, Reinbacher, and Overoth who did the actual early implementations for this in Quintic. So what we did was to take that algorithm and see, well, whether you can select points and just guess what the higher degrees would be. And that would actually, that sped up the Donaldson algorithm by to tenfold in terms of predicting the convergence. So that's a kind of fun thing to do. Lots of progress in the string algebraic geometry community, and then there are some really interesting ideas by Hashimoto, Halvorsen, and these people where they're beginning to actually interpret quantum field theory and string theory in its various guises themselves as neural networks. I'm not too familiar with this train of thought, but I think it's certainly a very interesting direction to follow. But what I got distracted by, so this is sort of the comma behind my talk. So this is good. So I have about 10 minutes. What about why stop at string theory? I mean, why stop at geometry? Why not just do every branch of mathematics problems to see how simple networks, or a simple feed-forward networks, I mean, nothing fine-tuned, or how support vector machines or base classifiers, how different problems in mathematics respond. And surprisingly, different branches respond in different ways. So this is a paper that I was working with Min-Young Kim. So we looked at various problems, but two that are which I find particularly interesting, which is one, if I gave you the Cayley table, if I gave you a Sudoku a table, can a support vector machine recognize this to be a Cayley table of a finite group? And that was fairly good, 95% of the time. So you can, of course, there's a known theorem to test this, but it's again an expensive one. What's more surprising to me was the following problem. If I just spat out Cayley tables at random, just a bunch of these, can you recognize the one which is a simple group? To do this from a Cayley table is hard. To do it from a character table it's much easier, but then you have to convert the Cayley table to the character table. But whatever the support vector machine doing, it certainly was not doing any of these sophisticated theorems. It was just basically doing pattern recognition of which ones are simple. Of course, we couldn't take too much data, so this is work in progress, because these tables get very, very big. So we only did a selection of tables, groups of order 8, 6, and 32, mix them all up, and then separate out the simple ones. So, but I didn't think this was going to be possible, because simple groups are very peculiar objects. But this is beginning to lead me to believe, at least this is a wild speculative belief, is that if you plotted the Cayley table of all finite simple groups in some high dimension, then it's not inconceivable that there exists some hyperplane which separates the simples and the non-simples. It would be really nice to find this high dimensional space and to find this hyperplane or hypersurface which separates the two. It's not inconceivable. I thought this would be absolutely impossible, but this is not inconceivable. So that's kind of, this would be a very, very curious way to do representation theory if this works out. So this is very much, we're still collecting data to make this plot possible. So other fun things, I'm not gonna bore you with all the various things. There was a fun thing I was doing with Yao, which is to just take the Wolfram database of finite graphs. And this I think I mentioned with Mike earlier, which is sort of the discrete version of Ritchie flow. So, but our initial motivation was this. But while we were working on it, we were just thinking, well, if I just gave you the adjacency matrix of a graph, and if it fed you enough number of examples, and enhanced them with permutation symmetries, just test the standard graphs, properties. Is the graph cyclic, acyclic? Is it planar? What is the genus? Is there Hamilton cycles? Are there Euler cycles? I'm just recording here the approximate accuracies at a 2080 cross validation. What is very interesting is this problem. Finding the Euler cycles in a graph is, I think, polynomial time. But finding Hamilton cycles in a graph is NP complete, because that's the traveling salesman problem. And they gave similar, they gave similar accuracies. At least, again, all of these were done either by very simple SVMs or by the kind of MLPs that I mentioned earlier. So it's kind of interesting that one is so hard and one is relatively easy, but the machine was both achieving a kind of mid-range accuracy. So maybe you can find a much more sophisticated network to distinguish the two. But
what's sort of the rough number of nodes you tried on this? Like,
yeah, so
how large are these graphs?
Yes, so I tried the entire database has all the connected graphs, which are familiar, which is in the literature, up to 100 nodes.
100 nodes. I see.
Yeah, so you just shuffle them up, and I think it's a database about 10,000 graphs, and then if you add in all the permutations, you can get something like a database of about 1 million graphs up to adjacency matrices, and you do cross validation on that. It's just kind of interesting that these two extreme problems were at this range of accuracy. Other things were much better. If you want to check, like quiver mutation, this is something else that Mike and I love so much. There you can do 0.9 to 100% accuracy. Just try to tell whether two graphs are cluster mutations of each other. So that's kind of interesting. So here's something that at least I was thinking that this would just have to fail, right? If you try to predict the next prime, that's just not going to work, because then I just end up breaking every single bank, and that is true. So if you try to train any neural you can think of, to predict what the next number is in the sequence, you're not going to get very far. So I even try things like a sliding window of the prime characteristic function. And just to predict, so you take a window of size, I don't know, 100, and of ones and zeros of whether it's binary or not, and train it up to say 1 million cases, predicting. So the output would be somewhere very distant, right? Or say a distant 100 away. Is that number prime or not? So you try this with an SVM. And I think I found that the result surprisingly wasn't bad. I mean, it was something like 0.7 or 0.6, 0.7. So it's not completely random. But if you want to try something like the Liouville lambda function, which I was told by the number theory community to be truly the hard one, and that's just how many prime factors. Is it an even number of prime factors or an odd number of prime factors? This problem has been challenged by Peter Sanak to be extremely difficult. It's one of the hardest problems handling number theory. And I tried on this one, try to do the prediction, and you get 0.5 accuracy, random guess essentially, and the chi-square of that is 0.0001, which is great, which is just like completely random distribution. Oh, I mean, it's not inconceivable that if I kept on working at it, I might find something, but that would mean that I will have to have stumbled upon some really deep theorem in analytic number theory in order to predict something like that. Similarly with the Birchton-Winton-Dyer conjecture, you don't get that kind of really good predictions. That said, surprisingly, in the last couple of months, I've learned something by working with my students at Hearst and Toby Pittican, and also with these are Kyo-Hwan Lee and Tom Oliver are card-carrying arithmetic number theory, arithmetic geometers, and so geometric number theorists. So we tried a bunch of other problems. So if you feed in the adjacency matrix and the permutation information of descent d'enfant and try to predict whether this graph is what is the transcendental degree of this Galois extension. This one I would have meant, well, primes and prime numbers are involved. This should behave really, really badly. But this problem is kind of 0.9%, but 0.9 accuracy, which was unexpected. And then we try to machine learn things like, can you tell whether an elliptic curve has complex multiplication just by looking at its L coefficients? And this problem was greater than 99% just by looking at a naive classifier, which is kind of unexpected. And then there's more recently we're doing this problem of just learning number fields. Just look at the coefficients of the minimal polynomial of an degree extension over the irrational over the rationals over Q. What is the degree and what is the rank of the Galois extension? And that also behaved very well. So some kind of arithmetic geometry is for some reason is certainly not as badly behaved as primes. So interesting. So let me just check on time. Sorry, I should stop. So I should wrap up. So let me skip. I did other fun things. Right, this is a fun thing. You know, we actually downloaded the archive. This is just to mention. We downloaded the archive titles to try to predict whether you know, there's. My motivation for doing this was: is it possible to generate enough syntax in the literature on the archive to predict what the next revolution would be? It would be great. So okay. I'll probably talk more about this in the question session, but this is not a joke because there was a paper just last July in Nature where they did exactly the same thing for chemistry, and they were able to actually predict a whole bunch of undiscovered chemical reactions that were much more efficient than anything in the literature. So this is I think this is really worth pursuing. This kind of analysis, but for shortness time, I won't get into that. So let me just wrap up. So this kind of ideas of machine learning mathematical structures is certainly useful for physics. Needless to say, but for mathematics, I was more thinking about, you know, what is the hierarchy of problems of difficulty. And we know there's a hierarchy in mathematics of difficulty where number theory is at the top and numerical analysis is in the bottom in terms of complexity, right? You know, you have things like Hilbert 13, which prevents any possible decidability in stuff like this, versus, you know, a very fast, you know, Newton's methods of convergence on here, and algebraic geometry is somewhere in between, partially because I think algebraic geometry over the complex numbers. Every computational problem in that is essentially about finding kernels and co-kernels of integer matrices. You know, no matter what problem in algebraic geometry is, and this is why people like Mike Stillman and Grayson wrote Macaulay 2. It's because they realized that almost every problem in algebraic geometry is about finding kernels, co-kernels of integer matrices, and that's something that's very amenable to the kind of machine learning paradigm. So. Just to flash a couple of more ideas, recently there's been a host of activities. You know, there's SciNet, and then there's AI Feynman, and symbolic manipulations, and there's this Ramanujan machine where people are thinking increasingly of how to use machine learning techniques to advance new ideas in physics and in mathematics. So I think I'll stop here. Thank you very much.
Thanks, Yang. Very, very interesting talk. A very nice historical context. A number of examples here. I'll open it up to questions.
I see some things in chat. I hope I haven't missed.
There were some comments by Jim Halverson.
Yeah, they were just asides that I threw in as. Yeah, there's.
Oh, I do. Jim's. Hey, Jim. I didn't even see your name.
Yeah,
What's up?
Awesome talk. Yang, great talk.
Yeah, that's right. That's absolutely right. So, Jim, and that's a very good. Thank you for first of all, thank you for what I've asked for. But you're absolutely right. The reason I think the prime window thing worked a little bit better than Liouville lambda is precisely because primes is in P, because of this HEW algorithm that came out a few years ago. You're absolutely right. I think it's kind of interesting that, you know. It
wasn't clear to me that it was exactly the same problem. I was just being a little.
No, it's not. It's not. But yeah. The fact that there exists, the fact that this is in P is kind of reassuring that this window is not doing completely random.
Right. Predicting the next prime is different than predicting your fixed integer is prime. But
yes, absolutely.
the way that you wrote it on the slide, primes is hard, just looks stylistically very much like the paper title primes is in P. Just with...
Oh, I see. Oh, I see. No, I see. Well, I just meant hard as in like life is hard.
Yeah, I know.
Yeah.
No, my serious comment was the one above it. That one was just an aside.
Oh, good. Yeah, great. Thanks. I'll have a look at that.
Yeah, so that some of the number theory story there and its connection in F theory has been worked out exactly for those 16 cases. And
Brilliant.
it turns out that the extra structures, so the elliptic curves associated with these 16 reflexive polytopes, of course, are not necessarily general cubics in P2. There are other ones and other toric varieties. And sometimes there are extra sections forced on you. And one of those actually gives you exactly the gauge with the standard model, complete with the hypercharge with the right charges of the U1. So just a cute aside that
No, that's interesting. See, one thing I wanted to always wanted to do is to compute the L functions for these 16, and to see whether they're special in some way, whether they're special modular forms. But because I have the equation, so I can actually compute its zeta function.
Yeah.
But I haven't gotten around to do it. Maybe it's interesting to just compute it and just see, or just expand it out to see what those coefficients are.
Yes, perhaps. That is not what this paper looks into. This looks into other stories, but
Right. No, cool stuff.
Let me. It's not quite a question, but it's a comment, and maybe will inspire an answer. So, I mean, you can ask. I mean, obviously, as a kind of as a physicist, one might say, I want an effective way to answer this question about my Calabi-Yau. Here's a very effective way. But one could also, of course, ask, so what are we learning from all of this? You probably get that question sometimes. And you could have different answers, and one of the answers might be, well, maybe there really is some sort of sense of the problem being hard or easy, or some sort of complexity theory of how problems can be solved in this way, which somebody will gradually will invent. But if that's the goal, it seems to me your problems are kind of underspecified, and what I mean by that is that. A lot of them, some of them are finite, but a lot of them have to do with, infinite data sets in principle, the primes or the graphs or the elliptic curves. And, it's not that you can't do a problem with an infinite set, but you're sampling, you have some kind of a distribution on which you're presenting this, sampling from this infinite set. And so really, the learning task could depend very heavily on that sampling. And of course, you could ask questions like, if you give it all little examples, will it ever extrapolate and work on a big example? And so that's a practical version of this. But for this question of, are you learning any kind of facts which could be explained by a complexity theory? Say, it seems like one should say how one's sampling, and one should not pick so arbitrary samples as Mathematica gave me this list, which is a good way to get started, but maybe not the most fundamental sample. And to ask questions like, well, to what extent do my results depend on the distribution? That's my
I mean, that's an interesting. I mean, this is very much, I think, in both up to both of you guys. You guys are be thinking a lot about this, which is sort of the statistical distribution of vacua within string theory.
The physics question, although that's right. I mean, in the physics context, one could go that way. I was more trying to ask the more open-ended question. What are we learning from this? And I think one could have an answer that says, yes, we're learning that this type of problem is easy and this type of problem is hard, and there's it's a complexity class. But you haven't specified a learning problem until you say something about the distribution that you're sampling.
Right.
Maybe I can ask a slightly related question if I understood Mike's. Sorry, were you going to piggyback on that and answer?
No. Go ahead. Yeah.
So on your last slide, you had some greater than symbols about complexity or something like that. Can you pull that up? So yeah. I mean, a related question that I'm sort of generally worrying about, as someone who spent like the first half of my career so far doing Calabi-Yau stuff and things that are relative to the things in machine learning, the things in string theory are very highly structured data.
Yes.
And you know, it's been kind of fun to work with more general instances of things and sort of start moving in that direction. But one thing I actually do worry about, I'm curious if you have any ideas on whether you worry about it too, whether you have any ideas about it, et cetera, is exactly the way in which, you know, all of the cases where we can actually compute anything are cases where, in principle, hard problems are made easier by algebraic geometry because of all of the extra structure we have in the game. And you know, whether that introduces some sample bias in our understanding of the landscape that, you know, potentially invalidates some of the things we've learned.
I see what you, okay,
Like this algebraic geometry stuff down your is pretty far down your complexity scale, just in the sense that there's so much extra structure in algebraic geometry compared to general Riemannian geometry and, you know, more general topology that I don't know, like I worry that it's like the string theory analog of just considering supersymmetric field theories, and that sample bias might put us in a case where we're just really not sampling what the world really is. But I'm normally much more optimistic than this, but
yeah, no, I think so. It's actually kind of interesting. I think, you know, the Corti group in you know, this what do they call it? They have a cute name, like some MC cubed. I don't know what any of those stands for, but what they're doing is following this minimal program for funnel varieties,
okay.
And they're now starting to machine learn that database. So this is no extra structure,
Right.
and just to say, let's classify, or, you know, go push as far as possible funnel varieties by rational transformations, and there they also see very distinct patterns.
Yeah. Yeah, I absolutely believe that, but they're still considering algebraic varieties, right?
Sure. Yeah.
Yeah. What are they doing actually? They're trying to carry out like a Mori program using machine learning or something like that?
Yeah, vaguely something like that, if I understand what they've been up to. Yeah, which is interesting.
Yeah, absolutely.
Yeah. So but I'm just saying, that's, I mean, of course, you know, all of these questions are open-ended, and I can't give any answers to this. So something that was very reassuring was to test the Liouville lambda function. How many, you know, just a sliding window of how many, whether the number of prime factors is even or odd. That I couldn't find anything. You know, I tried every neural network well, at least I knew, and I encourage people to find it. And you could not break Sarnak's prediction that this is probably one of the hardest problems. And it looks, if you just look at this data, it doesn't look any different from, you know, it's bunch of zeros, strings of zeros to ones going to 0, 1. And if that problem came from, like, say, adjacency matrix of graphs, chances are you're going to find a pattern very, very, very quickly. And surprisingly, if you do this problem not with Liouville lambda, but with primes, you know, the prime characteristic one, and immediately you jump to, well, not great, but something that's definitely not random anymore, which I think does have something to do with the fact that primes is in P. Other things, so something that was surprising to me was, so no, adjacency matrix and stuff like that, that's okay, that's almost imaginable, it's okay. But this kind of stuff, you know, but to be able to read out, you know, ranks of elliptic curves by looking at its L coefficients, I wasn't expecting that to do well, but yet it was surprisingly doing well. I mean, and I wasn't fine tuning. You know, I wasn't using, okay, I'm gonna do this particular convolutional network to home into this particular thing. I was just throwing generic things like naive Bayes classifier, decision tree, feed forward MLPs, a couple of layers in ReLU. And that all of them did very quickly to 0.9 and above accuracy. So there was something that was a manageable pattern in that. And I think you guys, I mean, you and Fabi were looking at, like, you know, solving Diophantine systems, right? Which you wouldn't have thought that would be, but these are particular Diophantine systems.
Yeah, we didn't do it with machine learning, but exactly. In that work, it was that the structure of the problem gave extra structure to the Diophantines that made them decidable. But yeah. Very interesting. I think Eric has a question. I'll be.
Yeah, sure. Is that
Well,
in chat?
I just wanted to follow up with Mike and maybe try to put it in a positive way. Are there further experiments that you could do? Oops, I'm black. There, here I am. Are there experiments that you could do with scaling some of your results to larger test sets than test sets with instances that are much larger than you trained on, in order to try to address this question of will my results obtained on finitely many instances of finite size, what does that tell me about the infinite limit? And you could see experimentally whether making it a little bit less finite tended to put you in the right direction or not.
That's a good question. I haven't tried, at least with any of these experiments, I haven't really tried extrapolating to that that far. I mean, I guess for the CC experiment, one thing that we did try, and then and this didn't do so well, was to train only on the tip, the small CC configurations for Hodge numbers to try to predict very large ones. That didn't do very well. But if you fed in like a couple of cases of the big ones, or I can't remember, like dozens of cases from the big ones, then you would do very well. So you kind of need that information. The ideal situation, I think that one was Andre did with Calum, which is to train bundle cohomology on a window where all of your numbers are bounded by something, and they trained only on those, and they extrapolate to ones outside of the window. And once they were getting 100% within the window, they were confident enough to try things completely outside of the training window, and that did work. And that's what I guess whenever that happens, you can raise a very precise conjecture. And this is something we did also here with Kilhuan and Tom. I can't remember the exact experiment now. We also did something similar. We only trained on near. Let me try to think of this. Something. I can't remember the details now, but we did the early coefficients, and never having seen the higher L function coefficients, and we try to extrapolate to that. And we're only able to do that because our classifier was working to 100% within this early training, this early period of training data. So I think this is a very interesting way of doing conjecture formulation. And if it does work, you could raise all kinds of new fun things.
Thank you.
Yeah.
More questions? Was there? Okay, why don't we thank Yang again for a very entertaining, informative talk.
Thanks for coming.
And so we're going to skip not just Thanksgiving week, but the week after. And then December 9th will be our last seminar of the semester, which is by James Gray, and it will be on numerical Calabi-Yau metrics through machine learning.
All right, okay, yeah, I've heard that they're working on this. So great, it will be great to hear.
Yes. I'm actually working on it too. I'm actually putting out a paper shortly.
Oh, brilliant! Oh, fantastic! Fantastic! Fantastic!
Okay, so everybody have a great Thanksgiving.
Happy Thanksgiving!
Thank you.
Soon.
Yeah.
And I hope to see you guys in person.
Yes.
At some point.
Thank you. This was really exciting. I wish you could have gone all the way to the end. I know you ran out of time, but thank you. Maybe
yeah, no, I mean, there's stuff. I mean, I think there's a lot of stuff to do here. I mean, in terms of this mathematics, it's just waiting to be done, and it'll be fun. It'll be great fun to do this.
Yeah.
Well, the funnest thing I've done here was to show that Vixra's syntax was not self-consistent. That was my. I was so happy to see that crackpots are truly crackpots in a syntactical way. So the confusion matrix for different sections of Vixra are different. Just from the title alone, you could tell that Vixra is a Vixra paper rather than an archive paper.
Wow. Oh, thank you. Yeah, maybe if you can just send the slides to Mike so that we can read the rest of it.
Sure, no problem.
Yeah.
Yeah, absolutely. Let me first make an important correct change. I meant I'm going to put prime numbers are difficult.
It just looked so much like the paper title that I had to give you a hard time. So.
You know, but I think what you say is exactly. I mean, this is the kind of I think that experiment with prime characteristic was much better than Liouville lambda. I think fundamentally it's got to do with the fact that primes are not primes is in P.
Yeah,
Must be.
I don't know much about this problem.
Me neither. I mean, other than the fact that I know there's an algorithm, and it's an elementary algorithm that essentially uses, Wilson's theorem. But they were very, very clever in getting that answer. It's amazing, right? It only came out like in 2006 or something.
Yeah, the primes is in P, you mean? Yes, that's right.
Yeah.
It's in the last 10 or 15
It's like
years.
totally crazy.
Yeah. I guess people expected it for a while, perhaps, but I think it might have been one of those problems that was known to be NP intersect co-NP, then, sorry, NP intersect co-NP, and then was shown to be NP, but I forget in detail. But I think one of the other takeaways that you're suggesting is sort of just like jump in and go for it. And
yeah, absolutely.
Yeah, I mean, it's actually pretty remarkable. I think this is a point you consistently made, that sometimes a few layer feed-forward network is all you need to get decent accuracy.
That's right. That's right. And a few layer feed forward usually performs just as well as an SMP.
Yeah.
So sorry, SVM.
Yeah. A recent data point from my own work that supports your conjecture is we worked very hard to phrase knot theory. Not actually, it wasn't that hard.
Oh yeah, your paper with Sergey. Yeah, that's a beautiful paper.
In a way that was natural from an NLP perspective. And it's very natural. It's kind of obvious. And we use this fancy new NLP architecture. But I think I used the NLP architecture before really doing the feed forward. And then I did the feed forward. I was already getting like 92, 93% accuracy there. So it was true that I got a, the NLP architecture covered half the distance between feed forward and perfection. But feed forward was already at like 93%. So it was like a 93 to 97% increase, but which is nice, but it's kind of amazing that feed-forward networks work so well on so many problems. So. Well, Yang, thank you so much. It was fun to hear.
That's great, Gracie. I guess I'll see you again soon.
Yeah, that's right. Absolutely.
It's like 2 weeks from now or something.
String data. That's right. So, all right. Cheers.
All right. Thanks a lot, guys. I'm going to. Great. So I'm going to stop. I guess I'll stop sharing.
Okay. Thanks again.
Yeah. Great. Great to see you, Mike.